So I think we decided that it was the CO2 plus that has the stronger pull on the electrons over the zinc because the voltage was lower, I think is what we said.
Does anyone from Carter's group want to confirm or?
He did say the smaller the voltage, it has more pull. I think that's what happened. It's a stronger pull.
Okay, so there's two different things that we're mixing up here, and we'll separate those out. One is relative between the two different cells, which pairing has more similar pull or more different pull. This question specifically says, which direction are the electrons? I was asking, which direction do the electrons flow? Meaning, what are our two half reactions? So let's start there, and then let's come back to the point that Alex and Carter made. So what are our two half reactions that are occurring when you put these two half reactions together and you connect them with a wire? Can I hear from Sydney McCann? Are you in a different group or same group?
I was in the same group.
Okay.
Are we talking about doing 12? Is that what we're 12 and
Yeah.
13 right now?
Exactly.
Oh, okay, gotcha.
So what are our two half reactions and how do we know what's happening at the cobalt half cell and what's happening at the copper half cell?
Did you
Lauren?
call on me?
Yeah.
Okay. So it tells us the electrons are flowing to the copper. So we know that that's gaining electrons, which means it's being reduced. And then reduction always occurs at the cathode. And then that's what is attracting the electrons. So for the half reaction, for copper, I have Cu2 plus aqueous plus 2 electrons produces solid copper. And then with the cobalt, it's being oxidized, so it's solid cobalt produces cobalt with a positive 2 charge plus aqueous plus 2 electrons.
Great. So the key to this reaction was if we know which direction the electrons flow, we know what's giving up and what's receiving electrons. So that's step number one. And I was telling my group that one of the things I really like about this is this particular approach is trying to say, based on what we see, we know that one has a stronger pull on electrons than the other. So if we look at which has a stronger pull on electrons, copper 2 plus or cobalt 2 plus, which one is it going to be? How do we know that here empirically or by evidence? So Aislinn, which one has a stronger pull on electrons? Which one of those two? And how do we know that?
I said that cobalt does, but.
So if cobalt had a stronger pull on electrons, wouldn't that be the one that's gaining electrons?
Oh, wait, you're not talking about number 15.
I'm talking about, I don't know if it's number 15.
14. Yeah, you're talking about 14?
Yes.
Sorry, I thought you were talking about 15. Okay, no, not what I said. The copper has
Great.
a stronger pull or attraction for electrons.
So we know the electrons are flowing this way, which means the copper has a stronger pull on these 2 plus ions becoming solid by gaining electrons. So then, Aislinn, how did you answer the next question? Question 15, which has a stronger pull between cobalt 2 plus and zinc 2 plus?
I said that I said that cobalt 2 plus has a stronger pull on electrons because the difference. One second, please. Sorry. Because the difference in the voltage or the difference in the pulling electron strength between cobalt and copper and zinc and copper was less than.
Fantastic.
Yeah.
So the voltage is exactly that. And so the voltage is a measurement of how different the pulling strengths are. So if you had copper 2 plus with copper 2 plus, your difference would be 0. You have no voltage because there's no difference in their ability to pull. The bigger the difference is in their pulling ability, the bigger the voltage is. And so 0.62 is less than the first cell we looked at, which is 1.10. And so I absolutely agree that cobalt, so if we talk about pulling strength, if that's a term, kind of a layman's term we're going to use, and that's what we're going to call, fancy term is reduction potential, that the one that has the strongest pull on electrons is copper 2 plus. So that one has a really strong pull on electrons. The next strongest is going to be cobalt 2 plus. And then the weakest are the ones we've looked at. Is zinc. Right? That kind of makes sense for which one has the best ability to pull electrons towards itself. So we just call that reduction potential. And the way that all these tables have been figured out is just by looking at what happens. They put them together, they say, oh, this one pulls electrons, and we can measure a voltage between those. The bigger the voltage is, the bigger the difference. And so electrons are always going to flow towards the one with the more powerful ability to pull those electrons. So if we then jump into our, there is some more stuff at the end of activity 50 you're welcome to do as practice. And then activity 51, this idea of reduction potential, obviously the one with the bigger number has the stronger pull on electrons. So what I want us thinking about now is, as we do our calculations, does anyone know if I love equations, or do I love or hate equations? I hate
You
equations.
hate them.
And the reason I hate equations is because people use them as a crutch. Instead of understanding the concepts, they just think about the crutch. So what I want to think about is, like we drew before, if you have something with really strong pulling ability for electrons, something with really weak, I want you to think about this as a number line. So we can have plus 0.34, we can have 0.0, and we can have negative 0.76. The further apart those things are from each other, the bigger the difference is in their ability to pull, the bigger the voltage is going to be. So if we compare these two to each other, which we've already done, we know that the voltage is 1.10. That's just how far apart they are. It doesn't, this equation up top, a lot of times people flip the sign, or they use, you can actually look up, instead of the reduction potential, you can look up the oxidation potential. It's the exact opposite sign. That's it. And so there's all these different ways to calculate it, but I really want you to think about reduction potential is the ability to pull electrons. How far apart are they on that scale? And that's the voltage of the cell. It's that simple. We have to figure out how many electrons are transferred. That's another thing now. So go ahead and work in your groups for about 5 minutes on activity 1, and hopefully we can kind of cruise through this and start working some of these questions. Tripty, which room are you in? Do you remember? You're muted. I unmuted you.
It was room 4, I think.
Okay, room 4. All right.
Dr. Bailey. You're on mute, by the way. On model, were we supposed to do model 2 of Chem Activity 51 as well?
Yes.
Okay. We got really confused.
Oh, really?
Questions on the table part.
Okay. So let's really briefly, I'm trying to look at the time and I realized we spent a little more time in that breakout room than I wanted to.
Yeah.
If we look at critical question number 2, do we know any of the electrochemical potentials in this table?
Yes.
Which ones?
We know copper and we know zinc.
Okay. Plus 0.34, minus 0.76.
Okay.
And standard hydrogen electrode, that's kind of our 0. And that's the model we skipped over, but that's a 0.
We're supposed to see your screen right now.
So if we know any one in a electrochemical cell, we can figure out the other if we know the voltage.
Right.
For instance, we know these two, and we know the voltage is 1.10. It's the difference, how far they are different from each other.
Right.
So if we go up to the top of the screen here, we can figure out a number of these by looking at the difference. And so we know that this is minus 0.76. So somehow bromine and negative 0.76 has to get us to 1.85. So what is, did I do that wrong?
So
I can't see your screen.
That would, yeah.
I'm getting confused.
What are you doing? I don't understand. Yeah, thanks for pointing that out.
okay.
All right, so if we know that we have 1.85 is there a difference between zinc and bromine, and we know that this is negative 0.76, then what does bromine have to be in order for that to add up to 1.85?
I got 1.09.
So 1.09, and I think that my group actually did this as well, and we did it wrong, because I want you to think about if we have 1.85 is the total difference, sorry, I should say is the total difference between two things. And one of them is at minus 0.76. No, we did that right, didn't we? Then it would have to be 1.09 would be the other one. Yes, so we're right. Sorry, I mixed myself up there.
You're all good.
1.09 to negative 0.76. That's a difference of the voltage of the cell, which is 1.85 difference.
Okay.
And we can do that for all of these in the entire cell. So then the question ends up being, what does that tell you about these different redox reactions? The bigger this number is for the reduction potential, the stronger that is at pulling electrons towards itself. So the one with the biggest reduction potential is going to be the one with the biggest pull of electrons. So we can pair anything together and make a galvanic cell we want. Depends, do we want a really strong pull of electrons or weak pull? So that's kind of where this activity was trying to get to. So with that information, Aislinn, do you feel comfortable figuring out the rest of them? It's kind of a process of elimination.
Yeah, I do, but okay, so are all anodes, they're all going to be negative?
No. So it's all cathode anode just describes, the anode describes the one with the weaker pulling power. So we could put two things together if we scroll down a tiny bit here. Come on, scroll down. So we just said that bromine is 1.09.
Mm-hmm.
So if we look here, this is 1.09 reduction potential, but we know the copper is 0.34. We could pair these two together, make a galvanic cell. What's the voltage of that one?
Would you just add those two together? No, you subtract them, find the difference.
You find how far apart they are.
Okay.
And so if one's a negative number, then it's further apart, right? So the voltage there is 0.75. In that case, copper is your anode. Anode.
Okay.
So anode doesn't mean it has a negative reduction potential. It just means it's the one with lesser pull of electrons out of that particular pairing.
Okay.
So all of this whole activity was really just to get us to say, to kind of look at, I don't even know if I'm going to do this chapter, how do I get to my book? To look at a reduction potential and to be able to say whether one has a stronger or weaker pull of electrons, and really to say that that's where all of electrochemistry is based around. And if we think about the reaction will pull electrons from one to the other, it forces one reaction backwards for one to go forward. That's all equilibrium. So if one is a higher potential to be stable by pulling electrons from the other, it's going to do that. But that's only because we're moving towards equilibrium. And so I don't know if I'm going to be able to, yes, I found it. I know we're way past time. Hemendra's going to be mad, and I apologize to you all for keeping you. The last thing I wanted to show was table 19.1 in your book. This is a standard reduction potential of every single half reaction that you'll ever run into for the most part. And so you can look here, the biggest half reaction is a plus 2.87. That's enormous, right? But that's fluorine becoming F minus, filling its octet. So some of these make sense, but if you go down and look through all these, you can take any of these and pair them together and you can make a galvanic cell and you can have electrons transfer, use that energy to then drive other reactions. Okay, so I just wanted to show you that. Thank you for your patience tonight. I know that we took a little while to get to where we were going, but on Monday's class, we're going to be specifically looking at how these electrochemical reactions are related to equilibrium reactions using E-cell, and we're also going to be looking at entropy and enthalpy. So hope you have a good rest of your week, and I will see you all either if you ask for me or on Monday. Stick around if you have any questions you want to ask.